Hello and welcome to this topic, the practical optimization problems. Based on the theory developed in the differential calculus, such as the first and second derivative test, Montanicity, concavity, etc., we can solve many practical optimization problems. We are going to discuss two of them in this section. Now let's see example 1. Suppose that a fish swims upstream with velocity v relative to the water and that the current of the river has velocity minus v sub c. The negative sign indicates that the current's velocity is in the direction opposite that of the fish. The energy expended in traveling a distance d up the river is directly proportional to the time required to the travel of the distance d and the cube of the velocity. So, what velocity v minimizes the energy expended in swimming this distance? Now let's solve it. So this figure illustrates the situation. Since the fish's velocity up the stream, that is relative to the bank of the stream, is v minus v sub c, we have that d equals v minus v sub c times t, where t is the required time. Thus, t is a quotient of d over the difference of velocity. For a fixed value of v, the energy required for the fish to travel the distance d is therefore like this. So the energy is equal to k times d over v minus v sub c times v cubed. We know that the domain for the function e is an open interval that vc to infinity. To find the value of v that minimizes the required energy, we set e prime v as 0 and solve for v. And we set e prime v as 0. We find the derivative like this. There are some factors, but the only factor we need to discuss is 2v minus 3vc. The only critical point in the interval vc to infinity is found by solving 2v minus 3vc is 0. And it's easy to solve that. This leads to v is 3/2 vc. The interval is open, so there are no endpoints to check. Here, the sign of e prime v depends entirely on the expression 2v minus 3vc, since all the other three expressions are positive. Now we can check. If v is less than 3/2 vc, then this factor is less than 0, so e is decreasing to the left of 3/2 vc. And if v is greater than 3/2 vc, then this factor is greater than 0, so e is increasing to the right of 3/2 vc. Then we can see that by the first derivative test, v is 3/2 vc yields a local minimum. Since this is the only critical point on the interval, this must give a global minimum. The velocity that minimizes the expended energy is therefore 1.5 times the speed of the current. Alright, so we found the velocity that minimizes the expended energy. Now let's see example 2. Imagine that there is a 6-foot wide hallway and it makes a right-angle turn. The question is, what is the length of the longest thin rod? Like this. What is the length of the longest thin rod that can carry it around the corner, assuming you cannot tilt the rod? Now let's see the model of the hallway. If the rod is too long, it cannot pass through, just like this, cannot pass through. And if it's too short, like this one, it's not what we want. So, what shall we do? What do you think about this problem? Please take 1 minute to think about it. Alright, Jonathan, do you have some ideas about that?
I think the time when the rod has the longest length would be when it forms an isosceles triangle with the outer walls, because at that time the rod would touch the inner walls. If it touches the inner walls before that, it will be too long, and the rod will be stuck. If it's too short, it won't be long enough. And for the length, when it forms an isosceles triangle, the height would be the square root of 2, and the area of that triangle would be 2. So the rod's length would be 2 times square root 2.
Alright, thank you, Jonathan. You give me so many ideas. Now let's do it together to see if your guess or intuition is correct, or if there are some other ways to solve that. Alright, let's see that the rod that barely fits around the corner will touch the outside wall as well as the inside corner, just like Jonathan mentioned. Now let's see this figure. As suggested in the figure, let A and B represent the length of the segment AB and BC, and let theta denote the angles that the angle DBA and the angle FCB. Consider the two similar right triangles, triangle ADB and triangle BFC. These have hypotenuse A and B respectively. And a little trigonometry applied to these angles gave that A is 6 over cosine theta and is 6 times secant theta. Similarly, B is 6 over sine theta is equal to 6 times cosecant theta. Note that the angle θ determines the position of the rod. And so we can find the total length of the rod in the figure is thus the length is equal to A plus B is equal to 6 times secant theta plus cosecant theta. So we find the function of the length of the rod. Then we can see that the domain for theta is the open interval that 0 to pi over 2. Then we can find the derivative of L is like this. And from this expression that we let L prime theta is 0, we can find that sine cube theta minus cosine cube theta is 0. And this leads to that sine theta equals cosine theta. We know that the only angle in 0 to pi over 2 for which sine theta equals cosine theta is the angle that pi over 4. We can find this in this figure. We again apply the first derivative test. If 0 less than theta less than pi over 4, then sine is less than cosine. See this figure again. So sine cubed less than cosine cubed. Thus, L is decreasing on 0 to pi over 4. Similarly, if theta is greater than pi over 4 and less than pi over 2, then sine theta greater than cosine theta. So sine cubed greater than cosine cubed, so the function is increasing. Then, by the first derivative test, theta is pi over 4 yields a minimum. The problem, however, asked for the longest rod that fits around the corner. As the figure indicates, we are actually finding the smallest rod that satisfies the conditions in figure 2. In other words, we are finding the smallest rod that doesn't fit around the corner. Therefore, the longest rod that does fit around the corner is L of pi over 4. Then we plug in pi over 4, we will find that it's about 12 times square root 2 feet and about 16 feet. Just now, Jordanson supposed that the width here is 1, so he get the answer that the length of the rod is 2 times square root 2, and this is the same as our solution because in our problem, the width here is 6. Alright, that means Jordanson's guess and intuition works. Sometimes when we take mathematics problem, we need to make a guess first, then try to prove that. It's a good way to solve the problem. Alright, that's all for today. Hope you enjoy it. And the next class, we are going to discuss the moving sofa problem. I look forward to seeing you next time.